Hello everyone, welcome to my channel Chemistry is Fun. In my previous video, I have discussed about the colligative properties. Today we will continue with that, and today we will study about the elevation of boiling point. Now just to revise once, let us see what are the colligative properties. Now you know that in a solution there are solute particles as well as the particles of the solvent. So those properties of solutions which depend on the ratio of the number of solute particles to the number of solvent particles are known as colligative properties. These properties are not at all dependent on the nature of the chemical species which are present. So now let us start about the elevation of boiling point. First we need to know what is a boiling point. Now the boiling point of a liquid is that temperature at which the vapor pressure of the liquid will be equal to the atmospheric pressure. So when vapor pressure of that liquid is equal to atmospheric pressure, that temperature can be called as the boiling point. Now if we make a solution in such a way that a non-volatile solute is added to the solvent, then there will be lowering of the vapor pressure. So for any liquid, the vapor pressure is lowered when a non-volatile solute is added. So when the vapor pressure is lowered, what will happen? So the temperature of the solution, when the vapor pressure can be equal to the atmospheric pressure, will be higher because the vapor pressure has already become low. So we have to make the temperature a little high so that the point will come when the vapor pressure will be equal to the atmospheric pressure. This temperature at which both the pressures will be equal will be higher than the temperature of the pure solvent, means when the solute was not added. At that time, if let's say at temperature T only the vapor pressure was equal to atmospheric pressure, now we have to find a new temperature T dash after addition of the non-volatile solute when the vapor pressure will be equal to atmospheric pressure, and this new temperature T dash will be greater than the temperature at which the liquid was boiling before addition of the solute. So now we find that both the temperatures are different, that is both the boiling points are different. This difference in boiling point for the solution and the boiling point of the pure solvent can be termed as elevation of boiling point. This is the elevation of boiling point. And if we plot a graph, for the vapor pressure against temperature, means for a pure solvent we take in the two axes, in one axis we take vapor pressure, in the other temperature for a pure solvent, and also we plot graphs for vapor pressure against temperature for two solutions, that is solvent and a non-volatile solute. We have to vary the concentrations and we plot three graphs now. One is for pure solvent and two graphs are for solutions having different concentrations. We find that the curves of the solutions will be situated below the curve of the pure solvent. Now how to explain that? We know that from Raoult's law of dilute solution we have already seen earlier, when vapor pressure of the solution was Ps at that time, we have seen it earlier. P0 minus Ps by P0 is equal to Wa by Ma into Mb by Wb. We have already seen this earlier. And if we shift Po to the other side, we get Po minus Ps is equal to Wa by Ma into Mb by Wb into Po. For pure solvent, Po is the vapor pressure at boiling point. Mb is the molecular mass and these are constant. So when these two are taken as constant, that is this one and Mb. These are constant. So if we remove this, we have to add this proportionality constant, sign of proportionality. We find that PO minus PS is directly proportional to WA by MA into WB. And this PO minus PS is delta P, that will be directly proportional to delta T, and here we can see that that is directly proportional to WA by MA into WB. Now to remove this proportionality sign, we multiply with a proportionality factor K. So delta T is equal to K into WA by MA into WB. So this K is the elevation constant. This is a proportionality constant for this situation. This is called as the elevation constant. Based on this formula, we can solve some numericals also. In case this WA by MA in this equation, if you take as 1, WB is equal to 1 gram, then delta T becomes equal to K. So when this full right hand part WA by MA is 1 and also WB is 1 gram, in that case, in this equation delta T becomes equal to K. So we can define that boiling point constant will be equal to the elevation in boiling point, that is delta T. Boiling point constant is equal to elevation in boiling point, which would be theoretically produced if 1 mole of a non-volatile solute is dissolved in 1 gram of the solvent. So from WA by MA we get number of moles, so that is 1, and also we are using WB is equal to 1 gram, so it is dissolved in 1 gram of the solvent. At that case, delta T, elevation in boiling point, is equal to K, boiling point constant. If WA by MA equal to 1 and WB is 100 grams, means in 100 grams we are dissolving, solvent is 100 grams, then delta T will be equal to K dash, new constant K dash called the molecular elevation constant, and K dash is K by 100. Because initially we were taking 1 gram, now we are taking 100 grams of the solvent. So here this new K dash, this term we have got, no, K dash, it is the molecular elevation constant. This is the elevation in boiling point which will be produced if we dissolve 1 mole of the solute in 100 grams of the solvent. And K dash into 100 is equal to K. So by cross multiplying we get this. Instead of K we can put in this equation we got earlier, no? In the previous equation which delta T is equal to K, that one. In K, if we put this new value 100 into K dash, we get delta T is equal to 100 K dash into WA by MA into WB. Here again we can find a new constant in case when WA by MA equal to 1 and WB is equal to 1000 grams, then delta T is equal to K by 1000, that is called KB. This is called molar elevation constant. Molar elevation constant is the elevation in boiling point when number of moles is same. 1 mole of the non-volatile solute is dissolved in 1000 gram of solvent. Here we are taking 1000 gram of solvent. This constant is also known as ebullioscopic constant. Ebullioscopic constant. This new K is equal to 1000 into KB. What is KB? Molar elevation constant or ebullioscopic constant. So here new we get delta T is equal to 1000 KB into WA by MA into WB. That is delta T is equal to molality into KB. So if you remove this KB, other parts it gives rise to molality. Molality into KB. So we can say that this molar elevation constant we got is a characteristic of a particular solvent, and the elevation in boiling point for a solution, in case it is non-electrolyte, that will be proportional to its molality. We can see from here. And equimolar solutions of all the substances, if we make it in the same solvent, they will give equal elevation in boiling point. So here solvent is more important. Molar elevation constant is characteristic of a particular solvent. Now we can go through a numerical example. The sum reads like this. On dissolving 10.8 grams of glucose, whose molecular weight is 180, okay, 10.8 grams of glucose, molecular weight 180, in 240 gram of water. See, this one we should write it as GM. 10.8 grams of glucose, molecular weight 180 into 240 grams of water. Its boiling point is increasing by 0.13 degrees C. We have to calculate the molecular elevation constant of water. So for this we have discussed the equation earlier. Using that only we will be solving. So first let us write down. We know delta T equal to 100 K dash into W by, you have to divide it by the capital W into small m. So from here what we get? K dash. We cross multiply. We see that K dash equal to delta T into W into M divided by 100 into W. Now we have to put the values first. According to the numerical, delta T is equal to 0.13 degrees C and W, that is weight of water, is 240 grams, capital W. And M is 180 given, and small w, that is we are dissolving glucose, so small w is 10.8 grams. Putting all these values, we can calculate K dash. So what we have to do? K dash is equal to 0.13 into 240 into 180. See, 240 will put here capital W, M is 180 we keep, divided by 100 into 10.8. We just have to do the calculation part. You find that after doing this calculation, we arrive at the value of 5.2 degree. We get 5.2 degrees. I hope all of you could understand the topic I discussed today, as well as you could appreciate the numerical done today. Thanks for watching my video. Thank you all. Please subscribe to my channel. Thanks.